Okay, in the last two videos, I showed how to prove an example using a direct proof versus a proof by contrapositive, a proof by contraposition. As you may have noticed, in this example, the direct proof was easier. I mean, in my opinion, it was easier. It was shorter, certainly. And the contrapositive proof kind of required that we dive into this weird stuff about, what does it mean for something to be divisible by 2? And, if 5n's divisible by 2, well, then it's got to be the n part that's divisible by 2 because it can't be 5. So, there's some reasoning here that we didn't really need to do. In general, when proving a statement, you have these, when proving a P implies Q, at least, you have these two options, direct and contrapositive, and sometimes one of them is easier than the other. But there's no telling which it's going to be until you try them. So here's my recommendation. I would usually try to prove something directly first, or at least consider proving it directly. Think about how that would go. Maybe try it and see how it goes. And if it seems hard, perhaps try proving the contrapositive of the statement, because sometimes that's going to be the easier one. So just bear in mind that you can always use either one of these two strategies. Now, this video, I actually want to introduce another proof strategy. So this is one that I have mentioned before because we kind of did a proof by contradiction back in earlier section. So proof by contradiction is a sort of a famous one. It has this beautiful Latin name. It's also known as reductio ad absurdum, which means reduction to the absurd, because essentially that is what you do in a proof by contradiction. You assume something which then reduces to a contradiction. The absurd is in reference to the contradiction, something absurd. So here's the idea behind proof by contradiction. And this can be applied not only to proving an implication statement, but to proving any type of statement. So I'm going to phrase it first more generally, and then I will give you a version of it, which is specifically for implications. So the more general version is to prove P, start by assuming not P, and deduce a contradiction, which I'm going to represent by the letter F for something false, right? And it doesn't really matter at what falsehood it is. It could be anything false, right? You assume the negation of the thing you're trying to prove, and from that, you deduce some kind of contradiction. As long as this negation leads to a contradiction, then the opposite must in fact be true, right? Because this can't be true if it leads to a contradiction. It's got to be the other one. So in other words, I'm going to write i.e. In other words, this is equivalent to saying P is equivalent to not P implies F. And this is an equivalence that you can prove. You can prove that. I'm going to leave it to you as an exercise to prove this equivalence. And that will kind of back up this idea of, back up as in support, this idea of proof by contradiction. So that is the sort of general version of proof by contradiction. Now, the specific version for a implication, it's the same idea, right? What we're going to do is assume the negation, not P implies Q, and then deduce, a falsehood. So assume the negation of P implies Q, but what is that? What is not P implies Q? Well, remember the conditional disjunction equivalence. We can rewrite P implies Q as not P or Q. One of the reasons that equivalence is so useful is because then it gives us a way to negate an implication statement easily, I guess. So this gives us a nice way to negate an implication statement. So if I apply De Morgan's law to this, to distribute the negation, it's going to become an and I'm going to also apply a double negative here. This is going to become P and not Q. So right there. So really what you want to do is actually assume that. You're going to assume P and not Q, and then you're going to deduce something false. One of the things that you could deduce, if you assume P and not Q, one of the things that you could deduce would be not P. So possibly deduce not P. Then you would have P and not P, right? Because you have P from your assumption. You would have not P that you deduced, and that's equivalent to false, right? So that's a contradiction. What this is showing, in other words, what this is showing is that not Q implies not P is sort of like a type of proof by contradiction. So in a way, and I'm just explaining this because I think it's interesting, and I think it kind of helps us understand what's going on a little better. In a way, this proof by contrapositive is, where did I first write it down? I first wrote it down here. This proof by contrapositive, where you assume not Q and deduce not P, it's kind of like, in a way, you could think of that as an example of assuming P and not Q and then deducing not P, which serves as a contradiction. So it's kind of like a type of proof by contradiction. That doesn't mean that it's exactly the same, but it's similar. So in the next video, I'm going to go ahead and show you an example of proving another theorem using this strategy.